Hello. So this is Pramod and I am going to tell you a system governed by the wave equation. This is the mechanical vibration class number lecture number 25. So let me introduce this system generated by wave equation, which is unit number 4. And in this system we have continuous system. In this model, the equation of motion of a continuous system or disturbed mass system will be derived using both D'Alembert principles and extended Hamilton principle. Different one-dimensional systems such as longitudinal vibration of rod, transverse vibration of string, torsional vibration of rod, and transverse vibration of Alert Bernoulli's beams will be considered in this model. So first we'll introduce you the continuous system. In the previous models, we have studied about the discrete mass system, where the model as the single or multi-degree of freedom system has been studied. In these cases, the system has a definite number of lumped mass, stiffness element, and damping elements. For example, the cantilever beam with the tip mass as shown in figure 10. This one in the below figure is modeled as a single degree of freedom system with a spring and a mass system. The spring constant, spring and stiffness constant K of the system was calculated using the following equation. The equation is equal to K equal to omega by delta, where omega by delta is given as a 3EI divided by L is cube. At W is the weight of the attract masses, and the delta is the deflection of the beam with the length L, and the Young modulus E, and the moment of inertia I. The natural frequency of the system will be calculated using the formula omega, and this is angular frequency under root K by M. So where M is the attached mass, in this calculation we have neglected the mass of the beam, hence it will be observed that by considering a point mass at the tip, we have considered one natural frequency of the system. Instead of modeling this system as a single spring mass, if one consider the beam to be consistent of several masses, then the system can be modeled as a multi-degree of freedom system as shown in the figure. But as the dimension of each elemental mass considered in this above cases is arbitrary, one may consider the beam as a continuous system with an infinite number of distributed mass and stiffness, and has infinite number of natural frequencies as shown in figure below. So in the contrast to the discrete mass system, in distributed mass of a continuous system, the system has infinite number of frequencies, and corresponding to each natural frequency, the system will have a distinct mode shape. It will be observed that the response to the continuous system, the response is only a function of time. Hence, while the equation of motion of discrete mass are written in the terms of ordinary differential equation, in case of continuous system, they are written in the terms of partial differential equations. It may be noted that by the real system or continuous system, a continuous system for analysis purpose can be reduced to an infinite number of discrete model. Each discrete model can be reduced to an eigenvalue problem. In case of continuous system, the solutions yield infinite number of eigenvalues and eigenfunctions, whereas in the discrete system, the eigenvalues and eigenvectors are finite. The concept of orthogonality is applicable to both the discrete and continuous system. In eigenvalue problem, the case of discrete system takes the form higher algebraic equation, and that equation will be given in the next slide. So the response of the system will depend on the boundary conditions. There are two different types of boundary conditions. For example, geometric boundary conditions, natural boundary conditions. Geometric boundary conditions are also known as essential or imposed boundary conditions, result from the conditions of purely geometric compatibility. For example, in case of clamped beam, in both the ends, deflection and slopes are 0. The figure is given below. The free beam bending moment and the shear forces are 0 at the both ends. Natural boundary conditions at the both ends will be given in the figure below. The natural boundary conditions are also known as additional or dynamic boundary conditions, which result from the balance of moment of forces in the boundary. For example, in case of a free beam, which may be a model of a flying aeroplane or a spacecraft at both ends, in this system shear forces and the bending moment are 0, and hence they constitute the natural boundary condition. In some system, one may find both the geometric and natural boundary conditions. For example, in case of simply supported beam, both the deflection and bending moment at ends point are 0. Hence, the boundary conditions in this case may be termed as mixed boundary conditions. Let us consider a specific example, a continuous one-dimensional system. This is the one-dimensional system where the beam, fixed beam is given, and the shear force diagram is given in this way. Here, the force and force balance and force equilibrium diagram is given over here. So, lateral vibration of flexible taut string. Strings are mostly used in musical instruments and many other applications of domestic and industrial nature. In a string of length L is shown in figure below, and which will be subject to tension T. Let at time T equal to 0, the string is pulled in the lateral directions, Y direction as shown in the figure, and left and the left. Hence, the lateral deflection along U along the string is a function of the space variable x and time t. So U will be given will be given a U, the function of U, x and t. If the lateral deflection is small, the change in tension T due to the deflection is negligible. The figure of that is given over there. The free body diagram of an elemental length dx of the string when the string is vibrating in the y direction, inertia force is acting. Considering the force in the vertical directions, applying Newton's second law of motions, the equations will be given written like this: dx by mdx in a dou u dot 2u upon dt square equal to t sine theta plus dou theta by dx into dx minus t sine theta. This is given, this is written according to the free body diagram in the previous slide. Here m is the mass per unit length of the string, and now assuming a small deflection u and slope q, the previous equation reduces to the following equations. And now substituting the slope theta equal to dou u by dou x in the equation 10.2, one may write the equations in this case. That means m dx upon d dou 2 u upon dt square equal to t dou 2 u upon dx square, dx m and dou u upon dt square equal to t dou 2 u upon dx2. So equation will be written in the differential equations that will be in a partial derivative equations like this. So here C will be the constant, C will be under root T by M, and above equation is also known as wave equation, and one may use a Hamiltonian principle to derive the equation of motion of this system also. So this system can be this system can be written using the Hamiltonian equations as well as D'Alembert principle. For the longitudinal vibration of rod, consider a rod of length L subjected to a force F at the time at t equal to 0. Then release it. It will be subjected to a longitudinal vibration. So you can see here the rod of elemental length dx at the distance of x from the one corner is written like is given over here, and the force F is applied longitudinally, and in this case there will be some change in length, and that's why some strain will be introduced over here. And since the force is applying and the cross-section area is there, so we can convert that force into the stress, and because of that stress there will be some longitudinal strain, and because of strain energy and the stiffness of that rod will pull down that force at the state of equilibrium. There will be some change. The force will be balanced by the stiffness of the rod, and then there will be some vibration in that rod. So that will be considered as a wave, and in this way the wave will be generated into this rod. So now we can calculate the longitudinal vibration of the rod. So in the previous rod we can see we have to derive the equations of wave introduced by the force applied on in the direction of longitude. So here from the Hooke's law we can write the P by A equal to E dou U by dou X, where E is the Young's modulus, and applying the Newton's second law of motion here, we can write that dm by dou to u by dt square equal to p plus dou p by dou x into dx minus p, and the equations will be, finally equation will be rho a dx and d2 dot to u by dt square equal to dou by dx and the root bracket e a dou u by dx upon dx. Now the same rod, considering the same elemental distance, elemental length, and we can just see here the force. If force will be the pressure will increase to the p plus dp by dx and dou x upon dx, and the same way the change in direction, change in the length will be du plus dou u over dou x in dx, where the p is the force at x, a is the cross-sectional area, is the Young's modulus, and dm is the elemental mass at the distance for the cross-sectional area dx, and rho is the mass per unit volume. So in this equation here you can see that means a into E is the constant. So longitudinal vibration in the same equations for the longitudinal vibration of the rod, the wave equations will be given as written as dou to u upon dt square e upon rho del u upon d2u upon dx2. This is the second order differential equation, partial differential equations. Here we can convert, we can change it to the c square e upon rho equal to c square. So where c will be under root e upon rho, and it will be observed that we are getting the same wave equation. In this case here only c is the different. It may be shown that c represents the velocity of the wave in the rod. So these are the books we have to follow, where the R.V. Ducipatti Advanced Mechanical Vibrations, and the textbook is William M. Thompson, Theory of Vibration with Applications. However, you can refer to the link which is written over here, and the NPTEL course, and with that we just end the longitudinal vibrations. If you have longitudinal inquiries on longitudinal vibrations as given as taught previously, so you can contact me at my personal address. That means I used to sit in the B127 right now, and you can come and just have a discussion about it. So this way, this is the last. So thank you. So right now what we have observed is basically the wave equations introduced into the rod, where rod is pulled by some force F, and because of that force the wave is generated into that rod, and we define that when just find the mathematical equations, mathematical formation of that rod, and based on then solving that differential equations, we can find the other related terms like angular velocity, angular axle frequency, and other things. So these things, so in mechanical vibrations you will find that means the solution of differential equations is very critical to understand the mechanical vibrations. So we expect that all of you must go through the differential equations, solving the differential equations, and it will be easy for us to find that means the mechanical vibration very interesting if you just try to solve it. Since I already told you that we have a MATLAB where you can just find the differential solution of differential equations very easily, and you can plot the graph, and physically you can see the amplitude as well as angular acceleration, angular frequencies. And if you can see that, if you just see that one of angular frequencies in just plotting into your computer, you'll find this very easy. So in the coming classes we'll talk about the few methods where we can few processes where we can just solve the differential equation in the MATLAB. So that will be you'll have some projects in MATLAB to understand that MATLAB and solve the equations in MATLAB. and with that we will have the great learning from this mechanical vibration. Thank you.